Engineering of Forces, Part 2. In the previous slide, we did explain some basic facts on the engineering forces for 2 and 3 forces in two-dimensional objects here. This is a continuation of that, and we exactly have similar assumptions to as we had before. Assumption number 1, the object here has a geometrical shape here. It doesn't have to be a proper regular shape, but it is in a two-dimensional. We do not assume as a point-like object or particle. Assumption number 2, all forces acting are in one plane of two dimensions. So here we assume a number of possibilities, or these are the only possibilities in which we have. Firstly, here non-parallel forces. So it means if, for example, we have got an object here, and this object, there are a number of forces acting in which they are not parallel to each other. And if these forces are in equilibrium, obviously they must meet at the same point. So it means here we assume if they meet at the same point. This is possibility number 1. So all these forces are now meeting at the same point. And the polygon is fairly easy. So it means you draw the parallel for each forces. One combination or one arrangement of this polygon is F1, then followed F2, then followed by F3, and then later on F4, like this one here, F1, okay, F2, and then F3 and F4. All of these certainly are parallel to the original one. If it forms a polygon, obviously it is in equilibrium. Although here, because at the start we assume in equilibrium, then it means they must form a looped or a closed polygon here. There are some other arrangements of this polygon here. One other possible arrangement is this: F1, F2, F4, F3, and definitely here you will get exactly the same solution, but just a different arrangement. Now, a simple question here: how many possible arrangements we have if we have 4 forces? Okay, do you think it is factorial 4 or different? So I will leave that for the reader to look at it, which is fairly easy. You can produce or introduce a formula for that. Now, vector notation, simply here as we had in our previous slide. In vector format, the algebraic sum of all the vectors, vector 1, F1, F2, F3 to F4 must be equal to 0, which is reflecting this fact. Now, each 2 forces, this is the second possibility here, each 2 forces meet at a different point. Imagine again here, this is an object. These 2 forces, F1 and F2, are meeting at this point here, and then F3 and F4 are also meeting at this point here, but definitely here in this case not all of them are meeting in one point here or at one point. Each pair is meeting at a different point. Obviously here, if I work out the resultant of this, if I name it R12, and we already assume that the whole system is in equilibrium, and if I work out the resultant of these 2 forces, then I must get to a conclusion that they are on the same line. Otherwise, definitely this is not compatible. So now there are 2 meeting points here in this possibility. And then polygon of forces looks like this. Exactly, we follow the rule. F1 is parallel to F1, and then F2 is parallel to F2, and then F3, and then later on F4. And we do have a similar situation. There may be some other possibilities. Okay, F2, then F4, then F1, and F3. I will leave it for the reader to write the rest of the other possibilities here. Now, result. So there may be some interesting results here. This is result number 1. If 4 forces are acting on an object, and if the object is in equilibrium, and if any three of these forces are meeting at one point, then the fourth force must meet at the same point as the other three. Otherwise, the equilibrium cannot be satisfied. Imagine, for example, these are three forces acting on an object here, and then these three forces, we assume they meet at one point, and then there is a fourth force. Although here, just for the purpose of simplicity here, we assume that this is not passing through this point here, okay, in which if you extend this line, definitely it will not pass through here, so it means the equilibrium cannot be achieved. Then it means this will be a wrong equilibrium. Then it means the force must be passing through the same meeting point. Otherwise, definitely the equilibrium cannot be justified. Vector notation, it is fairly easy, the same as we had before. Vector of F1 plus vector of F2 and F3 and then F4 equals 0. Now the next possibility here, parallel forces. So we assume here that we have got still four forces, and those four forces are acting in parallel. Like this one. This is just an arbitrary one, so you can draw another one in which all the forces are like this, okay? But now the question is whether we achieve equilibrium or not. This is the main point, okay? The resultant of these two, F1 and F2, we assume is R12, and the resultant of F3 and F4, we assume R34. And then certainly if this is in equilibrium, now they both must lie on the same line. Otherwise, the equilibrium cannot be satisfied. So it means this is the case of parallel here. 3 points to be noted. Firstly here, the resultant of the forces as we just explained it. Okay, they must be the same and line in opposite on the same one. Polygon of forces. Polygon of forces could look like this. Okay, here for simplicity, I'm just drawing it as if there is a space in between them, but in reality, this must be the same line, but in opposite direction. So you have got a triangle with 0 angle or polygon with 0 angle and 180 degrees. Point number 3, the exact location of the straight line in which both they meet. On here, this line is perpendicular to all, will be dealt with if you use moment. So it means these distances or perpendicular distances are known. Then we can calculate where exactly here, in which this is not the scope of this discussion here, but can be calculated easily. An example here in real practice, imagine for example you have got a beam, and this beam is supported by two supports, and this is just two weights or two loads acting on here, and these are the forces generated by the support. So these two are parallel, these two are parallel, the system is in equilibrium. Vector notation, still we have the same as before. Now result number 2. Result number 2 is parallel rule. Parallel rule is fairly easy. If four forces are acting on an object, and if the object is in equilibrium, then at least one force must act in opposite to the other two forces and in between them. Otherwise, the equilibrium cannot be achieved. Simply here, imagine for example, these are the forces in which they are all parallel. So it means now these are the lines or the extension of the line of the forces. But now you notice that these two are parallel in opposite to these two, but because at least one of these forces is not in between here, then it means there is no way in which this object is in equilibrium. So it means then this is a wrong equilibrium status. Then the correct equilibrium status will have to be like this. So now if you notice that that one here has to be in between those two. I'm not saying that equal distance. Definitely the distance y depends on the value of the forces, in which can be calculated separately here. So it means this is a correct diagram here. Now obviously here, like if for example we go back to the previous example here, this is a beam. If you have got those two forces, and if you have got those two forces, and then if none of these forces is in between, obviously here this is generating a moment and the system will rotate. The system cannot be, here the object is this beam, cannot be in equilibrium. But now this is a correct one. Now mixed case. Mixed case is you have got some forces are parallel and some forces may not be parallel. Like this is an example, like these two forces are not parallel, but these two other forces in which here certainly they meet at this point, okay? And then these two forces are not in parallel. And again here, realistically speaking, if we work out the resultant of these two and the resultant of these two, obviously these two resultants must pass on the same line, otherwise this cannot be possible. But in here there is only one meeting point. There is only one meeting point, and the next one is generated from the other one. And diagrammatic wise, the polygon looks like this: F1 parallel to F1, 2 the same, and then here. So it means this look like this. Another combination or another arrangement of the diagram could be like this one. Still this is true. But in here, if you look at it, it does not form a polygon here. It forms two triangles, which still is correct. Result number 3, if four forces are acting on an object and if the object is in equilibrium, it is impossible that only 3 of them are in parallel without the fourth one. This is also another fact here regarding the 4 parallel forces. F1, F3, and F4 are all parallel. But if, for example, here this object is in equilibrium, but F2 is not parallel to them, this cannot be possible. And then certainly here, F2 also must be parallel to the others. But definitely this is a condition or necessary, but may not be enough to tell if the system is in equilibrium. So one has to be aware of that, because the equilibrium depends on the distance and the values of those forces in which we have. 5 forces. 5 forces here simply, if you have got 5 forces, and then now the question is, this is the polygon in which we have, but definitely I will leave some interesting results to look at it yourself. For example, now the maximum number of the meeting forces will be equal to 3, so we cannot have more than 3. I will leave the proof or the demonstration for yourself. Parallel rule can also be satisfied here. If all 5 forces are parallel, the 2 outer forces must be in the same direction. Otherwise, the equilibrium cannot be achieved. And this fact is true for how many number of forces you have. At least one force must be in opposite to the rest. If you have got 4 of them in the same direction, at least one must be. And then definitely here must be in between them, because this is parallel rule. N forces here simply, if you have got n number of forces, this is force 1, this is force 2, this is force 3. So I would like you to generate a generic formula here if you have got n forces. So it means what is the maximum number of meeting points we have, in which certainly